You see them everywhere, holding back hillsides, shaping our highways, and creating level ground in our backyards. They seem simple, just a wall. But behind that facade is a life-or-death battle against an invisible, unrelenting force, the pressure of the earth itself. A poorly designed or built retaining wall isn't just an eyesore, it's a catastrophe waiting to happen, leading to bulging, cracking, and ultimately, a catastrophic collapse. So how do you build a structure that can confidently hold back thousands of pounds of soil, season after season, through rain, frost, and time? The answer lies in understanding the different types of walls and the fundamental engineering principles that make them work. We're digging deep into the world of retaining walls, from the simple gravity wall to the complex engineered systems, to give you the knowledge you need to choose, design, and build a wall that won't just look good but will stand strong for decades. Let's start with the fundamental force every retaining wall must fight. Lateral earth pressure. Soil isn't just a dead load sitting there, it exerts a horizontal push. And this pressure increases dramatically the taller the wall gets. The type of soil is critical. Coarse-grained gravel has a lower pressure than fine-grained, waterlogged clay, but the real enemy is water. Hydrostatic pressure. When water builds up behind a wall, the pressure can skyrocket, which is why so many walls fail after heavy rain, the single most important feature of any retaining wall, regardless of type, is drainage. A pro tip from site engineers that is non-negotiable: you must always include a free draining backfill material, like clear gravel or sand, behind the wall. And within this gravel, you must install a perforated drain pipe, or weep holes, at the base to collect that water and channel it safely away from the wall. Ignoring drainage is the #1 cause of retaining wall failure. It's not an optional extra, it's the core of the system. Now, let's look at the different types of walls, starting with the simplest, the gravity wall. As the name implies, this wall uses its own massive weight to resist the soil pressure behind it. It's typically made of heavy materials like large stone, concrete blocks, or even mass concrete. The cross-section is usually trapezoidal, wider at the base, to improve stability and prevent overturning. For a few feet in height, a simple interlocking concrete block system can act as a gravity wall. But here's a common and costly mistake: assuming every segmental block wall is a gravity wall. As the wall gets taller, the soil pressure increases exponentially, and the weight of the blocks alone isn't enough. This is where you must step up to a more engineered solution. For taller walls, from about 4 to 25 feet, the cantilever retaining wall is the industry workhorse. This is an L-shaped reinforced concrete structure. The vertical stem holds back the soil, but the magic is in the horizontal base, or footing. This footing is divided into two parts: the heel, which extends back under the retained soil, and the toe, which extends forward. The weight of the soil sitting on the heel provides a counterbalancing force that helps resist the overturning moment. The entire system is heavily reinforced with steel rebar, especially at the junction between the stem and the base, which is the point of highest stress. A major workflow secret is using structural analysis software like Orion or ETABS to calculate the exact size of the footing and the required rebar schedule based on the soil properties, and surcharge loads like a driveway or building near the top of the wall. They work by cantilevering from their embedded depth. Layers of synthetic geogrid are placed between compacted layers of soil. The geogrid grips the soil, creating a reinforced block that is actually stronger than the soil itself. The facing. which can be concrete segments or even gabion baskets, is largely cosmetic. The real structure is the reinforced soil mass. A pro tip for specifying geogrid is to always follow the manufacturer's charts for embedment length, which is how far back the grid extends into the soil. It's critical for creating the necessary friction and resistance. Finally, let's talk about construction sequence and common pitfalls. A catastrophic mistake is using the excavated, native clay soil as backfill. It holds water like a sponge and will guaranteed fail. The backfill and compaction must be done in thin lifts or layers to ensure density and avoid creating voids. In conclusion, a retaining wall is a system, not just a product. It's a careful interplay of the right wall type, impeccable drainage, proper reinforcement, and precise construction. Understanding the difference between a simple gravity wall and a cantilevered or a messy wall can save you from a devastating failure. It teaches us to respect the immense power of the earth and to build with a strategy that works with the soil, not just against it, as a critical safety and responsibility disclaimer. The information in this video is for educational purposes only. The design of any retaining wall over 4 feet in height, or any wall supporting a surcharge like a driveway or structure,